Good day everyone, my name is Jalaluddin. I am pleased to present our work titled Learning-Based MRI Response Predictions from OCT Microvascular Models to Replace Simulation-Based Frameworks. This research was conducted at the United Arab Emirates University in collaboration with École Polytechnique de Montréal. In this presentation, I'll provide an introduction to our research, detail our methods, share our results, and conclude with future directions. Let's begin with some background. Optical coherence tomography, or OCT, is an advanced imaging technique that operates on the principle of low coherence interferometry. It creates detailed cross-sectional images of biological tissues at the microscale by analyzing differences in light interference patterns. OCT has become invaluable in capturing brain vascular microarchitecture, which is critical for experimental studies focusing on cerebrovascular diseases. Computationally, we can use OCT angiograms to generate geometric models of cerebrovascular networks. These models are vital for understanding cerebral blood flow and brain oxygen transport. Fully resolved mappings of oxygen quantities across microscopic cerebrovascular models can help study neurovascular coupling, neurometabolic activity, and neurovascular diseases associated with oxygen transport deterioration. However, current methods face significant limitations. Simulation-based frameworks for quantifying MRI response require intensive geometric modeling of vascular structures and fully resolved mappings of associated physiological parameters. This process necessitates the tedious manual efforts and advanced image acquisition setups, making it impractical for large-scale or low-quality studies. Moreover, experimental studies focusing on some neurovascular diseases such as microstrokes often involve invasive protocols that disrupt blood microcirculation and are associated with microbleeds. In these cases, generating geometry-based physiological models of cerebrovascular networks become extremely challenging, if not impossible. These limitations in simulation-based MRI predictions underscore the need for alternative learning-based schemes for quantifying MRI response. We need more scalable, non-invasive, and efficient methods to quantify MRI response from cerebrovascular changes. To address these challenges, we propose using deep learning as a solution. Specifically, we aim to utilize 3D neural network architectures to predict MRI signatures from OCT angiograms. This approach has the potential to overcome the limitation of simulation-based methods. Our research objectives are threefold: to investigate the effectiveness of the state-of-the-art neural network architectures in predicting simulated MRI signatures. Secondly, to train these networks using structural and physiological components of vascular unit samples extracted from OCT angiograms. Thirdly, to validate our approach against traditional simulation-based methods for accuracy and scalability. Now let's look into our methods. Our approach involves several key steps: dataset preparation, model architecture selection and modification, model training, and evaluation. For our dataset, we created 5 OCT-based vascular stacks, each acquired from a different mouse. The average dimension of these stacks were 512 by 512, and each stack contains 300 slices with anisotropic voxel spacing. We systematically divided each stack into smaller, manageable subgraphs to ensure a detailed analysis could be conducted on distinct segments of the vascular network. We extracted subgraphs with a minimum of 30 nodes to maintain structural integrity essential for accurate simulation and analysis. And the size of these subgraphs were 64 by 64, and each subgraph contained 64 slices. Using the subgraphs, we simulated the MRI response using a spin echo sequence. The generated MRI signals from these subgraphs constitute our ground truth data. For input to our 3D regression models, we created image-based representations from the original graph models. We employed cylindrical models with varying radii to accurately map each subgraph segment to voxels within these images. Consequently, for each subgraph sample, we generated 9 image channels capturing essential features such as the binary image, magnetic field gradient, hematocrit, oxygen saturation, partial oxygen pressure, velocity, and velocity components along the X, Y, and Z axis. This multi-channel image representation reflecting realistic vascular and hemodynamic conditions constitute the input for our predictive model. We employed 9 state-of-the-art 3D neural network architectures from the MONAI framework, including autoencoder, basic UNet, dense net variants, efficient net variants, regressor, which is based on the ResNet architecture, and vision transformer autoencoder. These networks were configured to accept our 9-channel 3D volumes as input and output a 50-element vector representing predicted MRI signals. We made necessary modifications to some architectures to ensure compatibility with our tasks, such as adding pooling layers or adjusting the final output layers. For training, we use 3,599 vascular subgraph samples with 399 for validation and 1,000 for testing. We experimented with various loss functions, including MSE loss, L1 loss, and custom loss, combining L1 loss with Pearson correlation and cosine similarity. We used the ADAM optimizer and implemented early stopping to mitigate overfitting. These models were trained for up to 300 epochs. To evaluate our models, we use several metrics such as mean squared error, mean absolute error, R-squared score, and explained variance score. These metrics provide a comprehensive view of each model's performance, allowing us to compare and evaluate them effectively. These box plots show the distribution of MSE and MAE values across our different architectures. The regressor, which is based on the ResNet architecture, stands out with its superior performance, showing lower and more consistent error distribution. Other models like autoencoder and basic UNet showed variable performance, with some demonstrating wider error ranges or more outliers. This table provides a detailed breakdown of our results. The regressor model significantly outperforms its counterparts across all metrics and loss functions. When using MSE loss, it achieves R-squared score of 82.84% and the lowest MSE and MAE values. Other models showed variable performance, with some performing well under specific loss functions but struggling with others, such as autoencoder, which is basically performing really well with our custom L1 loss function. However, it performs poorly with L1 loss and MSE loss. This graph compares our model's predictions to ground truth data for densely populated subgraphs. The regressor demonstrates exceptional predictive proficiency, closely mirroring the ground truth. This highlights the sophisticated feature extraction capabilities in handling complex neurovascular structures. Other models like the autoencoder and basic UNet showed reasonable performance but didn't match the accuracy of the regressor. The vision transformer autoencoder offered a competitive results, suggesting its potential in handling dense data structures. Here we see models' performance on sparsely populated subgraphs. Again, the regressor maintains its high accuracy, adapting well to less dense data. Interestingly, the autoencoder shows limitations in capturing nuances within the sparser graphs, indicating its reduced adaptability to variations in data density. The vision transformer autoencoder performs relatively well, suggesting an intermediate capability in extracting features from less dense structures. The dense net and efficient net families underperformed in both scenarios. In conclusion, we have successfully trained 3D neural network architectures to predict MRI signal responses from microvascular OCT volumes. The regressor model showed superior performance, achieving a mean MSE of less than 1% and mean MAE of less than 4%. This work opens the door for scaling up experimental studies on microvascular disorders. Future work will investigate predicting other MRI sequences and exploring 3D-based deep regression models for studying variations in MRI effect size due to neurovascular deteriorations. This work was supported by internal funding from the United Arab Emirates University under grant numbers 12T037 and 12R239. We are grateful for their support, which made this research possible. Thank you for your attention. I hope this presentation has provided valuable insights into our work on learning-based MRI response predictions from OCT microvascular models. I'll be happy to answer any questions you may have about our research methodology, results, or future directions.